All right, our first video lecture is on related rates, section 3.9. Now, related rates is basically the word problem. So, of course, that's going to be a little bit more challenging than most, but we're going to go problem by problem, step by step, and we'll break this thing down into something kind of mellow. So there's going to be some steps through this, and again, like I said, these are word problems. So you have this PowerPoint, so let's get into it. We're going to move right into our steps, where we're going to get a word problem. We're going to try and draw a picture if we can. Certainly, we're gonna want to look. So we're talking about rates, so that's going to be with respect to time. So which sort of rates are we looking for? Then we're going to create some equations. We're going to use our substitution method sometimes, and then of course, since we're in calculus, we're going to need to differentiate. Then we'll plug in some values and we'll use our proper units to solve. Now, none of this will make sense at the beginning, but I want you to be able to refer back to the second page when you're going through any one of these problems. Again, like I said, they're challenging, so you need to really break them down to step by step, reread things. Let's just try and keep this thing as mellow as possible. But remember, we'll start off with kind of drawing a picture, maybe do something I call defining your variables, and we'll get this thing figured out. So we begin our first problem. And this is the classic. It's in every textbook. You've already actually had it in your homework, and we've discussed in one of the classes. My 2 p.m. class, someone had asked me about this, and it's the ladder falling. And this has to do with the rate and the time. So let's read it. A ladder 13 feet long. That will not change. There's going to be no change in that piece. Rests on horizontal ground and leans against a vertical wall. We know what a ladder looks like against a wall. The foot of the ladder is pulled away from the wall at the rate of 2 feet per second. Okay, that's a rate, just like miles per hour or anything that, like, you've been in a car, right? So you're changing distance with respect to time. So it says the ladder is pulled away from the wall at the rate of 2 feet per second. How fast is the top sliding down the wall when the foot of the ladder is 5 feet from the wall? All right, so let's make a picture. That's going to be the first thing we want to do. So let's just jump over here, and I already have something kind of written up. And here it is. Just made a little XY. Made something that's 13 units long. Just kind of made it there in purple. And it says that, well, we got this ladder. And once again, it's 13 feet long. It rests on horizontal ground and leans against a vertical wall. The foot of the ladder, right? That's not the top, that's the bottom. The foot of the ladder is being pulled away from the wall at a rate of 2 feet per second. So we're saying that this is going, the foot is going to go at 2 feet per second. I think that's a change in x. That looks like that's a change in x, how fast. When we're talking about a derivative, it's the change in something. Right now we're talking about, well, what's the change in our x value with respect to time? And that's 2 feet per second. So let's write this down. Let's just say that the change in x with respect to time is equal to 2. Let's put it in feet per second. Okay, we have our first rate. We found a rate. You can always tell because it's going to have division by time, right? Miles per hour, feet per second, meters per second. So let's continue going. And now it's asking, how fast is the top sliding down the wall when the foot of the ladder is 5 feet from the wall? Excuse my kitty, she likes to make a lot of noise. So then we also have, the question is asking us, how fast is that y value? The change, what's the change in y with respect to time? And that's what the question is asking us. It wants to know how quickly is the top of the ladder falling as our x value is changing by 2 feet per second. And the last piece is saying when, and we have to be very careful with when. The when means wait. When equates to wait. So we're going to wait on when the foot of the ladder is 5 feet from the wall. That would mean when x equals 5, but we're going to wait on the when, okay? When you see the when in the problem, just wait. We're going to plug that thing afterwards, all right? All right. So we got our when equates to weight for x equals 5. We're looking to find that change in the y with respect to time, our dy dt. This is what we're looking for. That's the big question. So now we need to go to our third step. Our third step tells us, let's go up and see it one more time. Our third step is telling us that, well, we want to create an equation that relates all the variables together. And this can be really one of the more challenging things that we do. So we jump back down, go over here. Now we need to come up with some sort of formula for this. Now, I think once you get used to it, this is a very common one. And this is x squared plus y squared is equal to, do I mean a squared plus b squared equals c squared? Well, shoot, that's what we're going to be looking at here. We're going to want to write in that our x squared plus our y squared is equal to the hypotenuse squared. But for us in this problem, it's 13 squared. That's never going to change. That's going to be 13 no matter what. That's how long the ladder is. So now we have ourselves an equation. We have an equation that relates everything together. We have our x values, our y values, and then we have this hypotenuse, I guess. So once we're here and we have an equation that relates all the variables, our dx dt, our dy dt, now we're going to go through and we will take a derivative on this. Now, all of these are chain rule. Every single one of these is going to be considered a chain rule. So when we take a derivative on 2x, we're going to say it's 2x, but now we're not going to say dy dx. We're going to say dx dt. That's the change in x with respect to time. That's what we're going to be looking for, and that's what we'd already found up top, that 2 feet per second. So we get to be able to plug that in. Now we're going to do the same thing with our y. Now the derivative on y squared is going to be 2y, and then dy dt. What we're looking for. And then we set this thing equal to, well, the derivative on a number, I think we all got that one down. That's going to be equal to 0. Well, at this point, we just want to plug in what we got and see what remaining things we may have. So we go back up and we look at our triangle. Let's start plugging things in. So we've taken a derivative. Our instructions say the reads, we create, we substitute anything that was necessary. That one we didn't need to substitute. Then we're going to differentiate with respect to t. There we go. And now we're going to plug in the when, and we're going to go and evaluate this sucker. So let's plug in what we got. 2 times our x. Well, that's when. That was that wait until after you take a dang derivative before you go plugging it in. So we're just plugging in for our x value right there. Times our dx dt. Well, we found our dx dt. That's right here. So we're going to multiply by 2. And then we say plus 2 times our y, and we don't have a y value. We're going to need to go find that thing. Now this is where the little bit of weird comes in. The little bit of extra. So when you go to plug everything in and there's still something that's missing, well, we might have to play a little bit of a game. So if we're to take our triangle from down here, just pulling it out of a piece, and it says that when, the hypotenuse was 13, the when, that was 5. Oh, there's our y value. A squared plus b squared equals c squared, so we can just go solve. So we have our y squared plus the 5 squared is equal to our 13 squared. Now hopefully you recognize this is a 5, 12, 13 triangle. So we have y squared plus 25 is equal to 169. A little bit of algebra, we're going to find out that y is equal to 12. Now we can just take that and plug it on in. We go through and we evaluate. Let's do some work. 2 times 5 times 2, that's 4, that's 20. Plus 24, there's that dy dt that we're looking for. And then this is equal to 0. Do some algebra. Color code. It's equal to 20. And we're going to find out that our dy dt is going to be equal to, that's 20 over 24, or 10 over 12, or let's call this thing 5 over 6. Oops, I forgot my negative sign. We subtracted over the 20, so our dy dt looks to be negative 5 over 6. And wouldn't that make sense that we would get a negative value? Isn't the y value getting smaller as our ladder falls away? Of course it is. It's going to be getting smaller, so that means the change should be negative. So we got an answer of negative 5, 6, but this is a word problem. Therefore, we're going to need to use, I hate to say it, but we're going to have to use words. So we go back and we want to use those proper units. So how fast is the top sliding down the wall when the foot of the ladder is 5 feet from the wall? We're going to say that it is moving at negative 5/6 of a foot per second. And that's really just how would you answer the question in words. You would say it with its units, and there is our solution.